Good morning friends, welcome to the chemical engineering series on mass transfer operations. The following are based on my understanding of McCabe, Treball and Kessler textbooks. I have simplified some concepts to fit into a storyline, so build upon the concepts on your own understanding also. Today we will be discussing about design of cooling towers, that is those large cylindrical structures with a wide base in a story mode. So in this story, our hero hails from a village where a thermal power plant is about to be erected. During the negotiation with the villagers, the board of directors says, if anyone finds the height of the cooling tower based on heat and mass transfer phenomena, all villagers will get suitable jobs. So our hero sets on a journey to solve the problem. The hero starts to break down the problem. I have no idea what happens inside the cooling tower, so let me ask someone. Hey, the water itself may have some idea. Let me ask the water. The water says, I don't know how to find the height, but I can help you understand what happens inside the cooling tower. So, when water and air are brought into contact, water evaporates into water vapor which diffuses into the insoluble air. So here there are a lot of concepts involved. Two main things are the keywords evaporates and diffuses. So this process which involves evaporation and diffusion is called as humidification. This is the another concept. So evaporation is heat transfer and diffusion is mass transfer. There is simultaneous heat and mass transfer occurring here. Now our hero has a doubt. Why does water evaporate in the first place? Because air has the ability to carry water vapor and is not saturated with water vapor. So here another concept comes in, that is saturation and the ability to carry water vapor. Okay. So had we not used a gas that cannot carry water vapor, for example like hydrogen, there will be no mass transfer, but cooling can occur via heat transfer alone. So our cooling tower may behave like a heat exchanger and not as a humidifier. So the presence of a mole difference drives the water vapor into air, which has a low amount of water vapor. So here another concept comes in, that is the amount of water vapor present in the air is called as humidity. So if air already had sufficient water vapor in it, no mass transfer occurs, but cooling can occur via heat transfer. But how does this mass transfer cause further heat transfer? The evaporated water takes some heat from the liquid water, and this heat is called as latent heat of vaporization. This is another concept, and this is the heat energy needed for the water to vaporize itself. So this energy taken away from the liquid water cools the remaining liquid water and brings in a temperature difference. So this can cause further transfer of heat. Now the hero has a doubt. If I have air and water at same temperature, then is cooling not possible? Water replies, cooling is possible even if air is saturated or temperature of water is lower than air. How is that possible? The only thing that matters is the gas enthalpy, which is the actual driving force. We will see this later on. So the cooling will occur if water contributes to heat of vaporization. Cooling will occur only if the liquid temperature is greater than the wet bulb temperature of the gas. This wet bulb temperature defines the driving force of the enthalpy. And this wet bulb temperature TW can be found easily by shaking a thermometer covered with wet cloth. And specifying this wet bulb temperature fixes the air enthalpy, and hence the amount of humidification. When the rate of heat transfer to liquid from air is equal to the heat needed for evaporation, then the steady state temperature is reached, and that steady state temperature is called the wet bulb temperature. Thank you, water, for your efforts. You have introduced lots of technical terms, but I have understood only a little bit. So let me investigate this humidification phenomena on my own. Let us now take a small break and then we will build upon the humidification phenomena. Thank you, water, for your efforts. You have introduced lots of technical terms. I have understood some. Now let me build up this humidification phenomena on my own. Distance from equilibrium properties determine driving force for mass transfer operations. So let me start with equilibrium characteristics of pure water packed inside a syringe with movable piston. At very low pressure, the molecules are far apart and so they exist in gaseous state. At high pressure, molecules are near and they exist in liquid form. For a constant pressure, that is, for a constant mass kept on the piston, providing or removing heat will change the phase and temperature of the constituents which are present inside. For multiple pressures, we can repeat this experiment and plot the pressure versus temperature or relative enthalpy versus temperature plots. In a batch process at constant pressure, as is the case with our syringe, the work is done only in expansion against pressure. So Q equal to delta H is equal to change in internal energy plus pressure multiplied by volume. Heat supplied or removed is the relative enthalpy here. First, let us plot the composition, that is vapor liquid equilibrium curve, which can be plotted as mole fraction or moles versus temperature or partial pressure or total pressure versus temperature. So assuming that we have started with the liquid state, as we provide heat, the temperature increases and bubble point is reached. That is, the water vapor starts to form. At this stage, there is no change in temperature, but the phase change occurs until all water evaporates into water vapor. Only then, the temperature of the vapor phase increases if we continue supplying heat. The heat associated with phase change is called latent heat of vaporization or condensation. This is an important concept. And the other heat associated when there is no phase change occurring is called as sensible heat. This also has to be noted down. For any gas beyond a critical temperature, no matter what pressure we applied, it cannot be liquefied. This is the gas state. At the critical point, the distinction between gas and a liquid state disappears. That is, they have identical density, viscosity and other properties. So this critical point is also another concept. Here water can be assumed to be in vapor or liquid state only, not in its gas state, and air can be assumed to be in gas state only, it doesn't liquefy at all. This assumption can be made in the present humidification system. In the second plot is the enthalpy H versus temperature. Here let us assume that we start with the gas stage and we are continuously removing heat from this syringe piston arrangement. So as we remove heat, it follows this path and reaches saturation vapor where the first liquid drops start to form. This is also called as dew point. At this point there is change of phase, but the temperature holds constant as all the vapor condenses into liquid. Once all the vapor have condensed into liquid and only liquid is present, that is called as a saturated liquid. And if we reduce the pressure or if we add slight heat, then the liquid is going to boil and evaporate. But here we are removing the heat, so the saturated liquid will cool along this path. So this also we can repeat at various pressures to find the loci of the saturated vapor and saturated liquid, and those two will intersect at the critical point, beyond which the gas state alone will exist. So we have plotted the pressure versus temperature as well as relative enthalpy versus temperature plots for pure water only. Let us now increase the complexity by adding air also. For this binary mixture, how can we define its properties based on the pure properties which we studied now? So for this, let us study some essential vapor-gas mixture characteristics. The essential characteristics that are required to understand humidification are humidity, which is the amount of water vapor present in the air. So for composition, we typically use mole fraction, but here the amount of gas, that is air, does not change. So we study the composition in terms of molar absolute humidity, which is the ratio of mole fraction of A, which is water vapor, to mole fraction of B. Thus capital Y is equal to PA divided by PB. Since it is a binary mixture, we have PA by total pressure minus the partial pressure. Historically, humidity is defined in terms of mass, that is mass of vapor per unit mass of dry gas. So the molar absolute humidity Y dash is equal to molecular weight of A into the molar absolute humidity divided by molecular weight of B. Here A represents the liquid water which can evaporate into water vapor. So B here is air. Hereafter, whenever we refer as humidity, it is with respect to mass. Thus, mole fraction small ya and y dash are related by this relation got by rearrangement. In the denominator, we can neglect the y dash by molecular weight term, and hence mole fraction is proportional to humidity, absolute humidity. When air cannot carry any extra load of water vapor, it is said to be saturated. That is, it has reached a limit of humidification. The humidity at saturation is given by this relation, where partial pressure is replaced by the vapor pressure. But normally we will use unsaturated gas for our humidification process. For this unsaturated mixture, we define the dry bulb temperature, which we normally measure using our thermometer. The relative saturation is defined with respect to the pure liquid property vapor pressure, partial pressure to the vapor pressure ratio. The percentage saturation is also a ratio to the saturation ability, but it involves the gas also via the total pressure. And percentage saturation is given by this. Both relative saturation and percentage saturation are useful to identify psychrometric curves. The percentage saturation is useful for interpolation of unsaturated enthalpy using enthalpy of dry and saturated air. The next term we define is humid heat, which is similar to the specific heat Cp, which is used in the heat balance, where mCp delta T is the energy term. But humid heat is for vapor gas mixture and is defined as the heat needed to raise temperature of gas and the vapor it holds by 1 degree centigrade. So humid heat Cs is equal to specific heat of the dry air Cb plus specific heat of water vapor multiplied by its amount, that is humidity. So Cs equal to Cb plus y dash into Ca. This is useful in finding enthalpy of the vapor gas mixture, which is defined as H equal to Cs into temperature of the gas minus reference temperature T0 plus the energy needed for vaporization of the water vapor, that is latent heat of vaporization into y dash. So here the Cs terms capture the sensible heat part and the lambda term represents the latent heat part. Thus, our hero has acquired the alphabets needed to describe humidification in mathematical language. Now our hero sets out to assemble the tools required to solve the air-water system. So the hero talks to various wise men and finally comes to know about an sophisticated tool called humidity or psychrometric chart. However, the wise men warn him that this chart is as complicated as knowing a woman's heart. So he requests one of the wise men to explain it to him, and the wise man explains as below. The humidity or psychrometric chart is a huge collection of equilibrium data. There are 3 thermodynamic paths, 5 family of curves, and lots of interdependent data. The 3 thermodynamic paths are: for isothermal process, we have to move vertically. For constant humidity process, we have to move horizontally. Finally, for adiabatic humidification process, we have to move along the adiabatic saturation curves at the respective saturation temperature. Since these adiabatic saturation curves are a bit complicated, we will see them later. The 5 family of curves are: 1. Absolute humidity versus temperature for various percentage humidity values. Second is the humid volume versus temperature. Third is the humid heat versus absolute humidity, and this humid heat values are present in the top left x-axis. The fourth is enthalpy versus temperature plot. This will be used in the final derivation, as enthalpy difference is the ultimate cause of humidification. Finally, the fifth one is the adiabatic saturation curve. Some of the data which we can identify in this chart are: if humidity y dash is known, the saturation temperature can be found by moving horizontally and then intersecting at the 100% saturated curve, and then moving vertically down to find the x value, which is the Ts. If humidity y dash is known, Cs, that is humid heat, can be found, and these humid heat values are on the top left x-axis. If dry bulb temperature and percentage saturation are known, humid volume and enthalpy can be found by interpolation in the vertical line segment, which is shown for the enthalpy curve around in this chart. If humidity y dash and dry bulb temperature are known, percentage saturation can be found by their intersection. Similarly, given any two, the third may be found. If wet and dry bulb temperatures are known, humidity y dash can be found as the intersection of the adiabatic curve at the given wet bulb temperature with the vertical line from the dry bulb temperature. This is how generally we will determine the humidity of a gas. My God, this is too much information to digest. Yes, I accept that this is a multi-useful chart like a pocket knife that can be used for various purposes. But we need some elaboration on the adiabatic saturation curves and wet bulb temperature. Oh, wise man, can you please explain those two topics? Adiabatic saturation curve is the path each point in our tower will follow, as it is also adiabatic in nature. To determine this path, we use a spray chamber saturator, where a vapor-gas mixture at temperature T is contacted with a sufficient amount of liquid which is at adiabatic saturation temperature Ts. The gas will be humidified and cooled, so Ts is less than T. If sufficient contact was provided, the gas will saturate. Based on the mass and enthalpy balance, we find that the sensible heat given up by the gas equals the latent heat needed to evaporate the water. That is, Cs into T minus Ts equal to lambda S into y dash S minus y dash. Rearranging this, we get the form of a line which starts at the saturation point Ts, Ys dash and has a slope of minus Cs by lambda S. This line is the adiabatic saturation line which we saw in the humidity chart. So they have the slopes of Cs by lambda S. Now our hero wonders how to find this Ts without performing this laborious saturation experiment. The wise man replies, fortunately for the air-water system, Ts saturation temperature is same as the wet bulb temperature Tw. The wet bulb temperature can be determined simply by shaking a thermometer whose bulb is covered with liquid-soaked wick. Here, when the rate of heat transfer from air to liquid equals the heat needed for evaporation, a non-equilibrium steady-state temperature Tw is attained. Heat transfer is given as the coefficient Hy times the temperature difference, T minus Tw. The rate of mass transfer is given by molecular weight Ma times flux in terms of mole fraction. For a stationary gas, the flux Na is given as product of a proportionality coefficient and the mole fractions. Further, we can approximate the mole fraction in terms of absolute humidity as Mb into Y dash. So using these relations, we get the equation of the psychrometric line as Y dash minus Y dash W by T minus Tw is equal to minus Hy by Ky lambda W Mb. From heat and mass transfer analogy, we know that Hy by Ky into Mb is equal to Cp or Cb into Sc by Pr power m. For air-water system, normally Cs is approximately equal to Cpb or simply Cb, and Sc by Pr, which is Lewis number, is approximately 1. Thus, the Lewis relation of Hy by Ky into Mb is approximately Cs holds true. And so, lucky for us, saturation and psychrometric lines overlap, as we can observe by comparing the slopes of these two lines. Let us now take a break here and summarize what we have learned. We have learned how to read data from the humidity chart, and then we have also learned two concepts of adiabatic saturation curve and the wet bulb temperature, which fixes the driving force. I hope you all, like our hero, have understood how to use the humidity chart, but we do not yet know where or when to apply this. With instinct as guidance, our hero proceeds to draw the equilibrium and operating curves for enthalpy versus temperature. Since for any mass transfer operation, difference between equilibrium and operating conditions provide the driving force. Let us assume a constant L value, as the change in L value is about 0.2 to 2% only. So, performing an overall balance at the inlet and outlet, we get the first equation, and then performing the enthalpy balance for the intermediate point and the entrance liquid, we get the rearranged operating line, Hy equal to Ha plus LCb by G dash into Tx minus Txa. Cl is the specific heat of liquid. So by observing this line, we see that temperature and enthalpy at the inlet condition of liquid gives the starting point, and slope is given by the flow rates and specific heat capacity of liquid. The minimum possible gas flow rate can be determined by drawing a tangent to the equilibrium curve from the starting point Ta, Ha, and then we can multiply by 1.2 to 2 times of that tangent value, and then we can plot the real operating line. So we have our equilibrium and the operating lines, but still we are not able to find out the number of transfer units or the total height of the column. We are unable to figure out whether we should draw steps like the McCabe-Thiele method, or should we integrate horizontally or vertically, or any other slope. So wondering how to relate the enthalpy with height, our hero falls asleep. In his dream, the cooling tower gives him a small piece of advice, which provides the clue to our hero to perform the analysis for a small differential element. So to relate the height with enthalpy, our hero sits down with intense focus and does the analysis. Hours later, our hero goes to the board of directors and says, "We have to integrate the inverse of the vertical distance between the equilibrium and operating enthalpy curves to find the number of transfer units required. Multiplying the number of transfer units with height of a transfer unit given by the manufacturer will provide us the height of the tower." This is the essence of our analysis. So with this, the problem is solved, but the board of directors, like a good engineer, asks our hero for the calculations. So let us now elaborate this derivation. So to relate height and enthalpy, we investigate the rate of heat and mass transfer for a differential element dZ, shown in the figure. Here, Na represents the molar flux, which has to be converted into mass, which in turn has to be converted into heat, and Ql and Qg represent the rate of heat transfer in liquid and gas parts. So in liquid there is only one heat transfer contribution, but in the air there are two contributions for heat transfer. One is the mass and one is the temperature difference. To quantify the mass transfer of water vapor into the air, we use flux, which is amount or moles per unit area into time. Here area is the cross-sectional area of the tower and not the interfacial area across which the water vapor crosses. The interfacial area per unit volume A is given indirectly by the tower manufacturer. So the interfacial area for dZ element, which is ds, is given by A into volume of the differential element. So ds equal to A dz into cross-sectional area. So this is the hidden trick here, which brings in the height of the tower dz. So mass of A crossing the cross-sectional area per unit time is Na Ma A dz. This is same as the vapor gained by air, that is G dash into dy dash. So simplifying the flux Na, which has a non-diffusing B component, Na is equal to the transfer coefficient times the mole fraction difference, and further the mole fraction may be approximated as y dash into Mb. Hence we get G dash dy dash is equal to Kya dz into Mb into yi dash minus y dash. Multiplying this by the latent heat of vaporization, we convert this mass relation to enthalpy relation. So the total heat transfer in gas is obtained by adding the above enthalpy relation of the newly added vapor to the heat transfer in the already present vapor gas mixture, which is due to temperature gradient. Adding and simplifying the total heat transfer in gas phase, we observe that integral of dH by Hi minus Hy gives the number of transfer units needed, but Hi is unknown. To find Hi, we equate the heat transfer rate in liquid to the total heat transfer rate in the gas phase. This says that the line connecting Ti, Hi on the equilibrium curve and Tx, Hy present on the operating curve has a slope of minus Hxa by Kya into Mb. Thus, for many points on the equilibrium curve, we can draw lines of this slope to find Hi minus Hy. Numerically, we then integrate the inverse of these values and multiply by G dash divided by Kya Mb to get the height of the tower. So this is the second approach. The first said method of finding H by simple vertical extension of points in the operating line to meet the equilibrium line at H star, and then numerically integrating the inverse of H star minus Hy to get number of transfer units is simple and is practically used. The number of transfer units is multiplied by the height of a transfer unit provided by the manufacturer, which is G dash by overall coefficient Kya. So this is how the manufacturer will provide us indirectly the interfacial area per unit volume A. The board of directors is impressed and offers a job with high salary to our hero. But our hero says, "Offer these jobs to my villagers. I have a job of my own." And the credit rolls. I hope this video, though lengthy, was useful to you in some way. Thank you.